Okay, so today's video is on types of symmetry, how to test for what type of symmetry it is, algebraic and graphically, and then also how to describe a function as even, odd, or neither, and what that means in terms of symmetry. So when we talk about symmetry, some of you may know this word already and be familiar, but when we're talking about this with graphs or algebraically, we're talking about either line symmetry or point symmetry. And so line symmetry uses the x-axis, so this is our x-axis here, and our y-axis as common lines of symmetry. So this is our x-axis, this is our y-axis, as common lines of symmetry. Point symmetry, however, uses the origin as a common point. So the origin, remember, is this point at 0, 0. So what this is saying is that if I flip this over the x-axis, so this, remember, this is my x-axis. So if I flip it over this line, it's the same here as here. It overlays itself. And with y-axis symmetry, this is our y-axis, I can overlay it over the y-axis and it will cover itself. And then with point symmetry, it's saying that if I rotate this graph 180 degrees around this origin point, it will overlay itself as well. So that's what it means graphically. But how do I learn what this means, or how can I prove what type of symmetry it is algebraically? So on your guided note sheet, you have a section that's titled Tests for Symmetry, and you've got a graphical test column and an algebraic test column. And so the graphical test, for every point xy, so in the x-axis column, for every point xy that I have, there is a point x, comma, negative y. And we kind of figured that out already on our x-axis symmetry graph. So if I'm looking at this point xy here, for the same x here, I'm going to have a negative y. So this point here is xy, this point here is x, negative y. My x value stays the same, but my y value is negative on that graph below. So algebraically, in this, you may have already guessed that when I replace y with negative y, so when I replace y with negative y, I result in equivalent equations. And so we'll see what that means in a little bit. But what that means is when I plug negative y in to an original equation for a graph for where y was, I'm going to get the same value in the end, in the resulting simplified equation. So let's move on to y-axis symmetry. So you might have already moved on. For every point xy on the graph, there is a point negative xy. And so you can see this here. This is my point xy. And then on this side, I've got negative xy there. So when I'm algebraically testing for this, replacing x with negative x results in equivalent equations. That one's really difficult to see, isn't it? There's my y. So then you might have also looked ahead at origin or point symmetry. So here I'm switching to negative y, here I'm switching to negative x. If I have a point xy here, what am I doing at both of these values to get into quadrant 3? I'm making them both negative, so I replace them with negative x, negative y. So this is a negative x, negative y. So I replace, for every point xy, there is a point negative x, negative y on the graph. So I replace x with negative x and y with negative y, and they result in equivalent equations. So we're going to look at that, what that means right now. So graphically, we've seen all this. So graphically, for every point for x-axis symmetry, for every point xy, there is a point x negative y. For y-axis, graphically, for every point xy, there is a point negative x, positive y. And then for origin, for every point xy, there is a point negative x, negative y. That's right here. So let's look now at algebraically how we test for these. So if we look at number 1, this is what it looks like. This is the graph. So look down at your example problems number 1. It says use the graph to determine if the relation is symmetrical to the x, y-axis, and or origin. And then it gives us a bunch of check boxes. And then it says confirm your answer algebraically. So we're looking graphically first to see, like, to give us a hint so we don't have to test every single problem. And with this one, I'm originally looking at if I have a point xy here, is it going to be overlaid over the y-axis? Is it going to be overlaid over the x-axis? Or is it being rotated around the origin? And this one really looks like y-axis symmetry to me, because it looks like it's overlaying, like it looks like if I was to take this side and overlay it over to this side across the y-axis, so I'm moving across the y-axis, it looks like it would overlay well. So in order to test this, we have to plug in negative x for our original x. So what that looks like is I'm going to sub it in, and I'm going to write y equals negative x to the 4th minus 4 negative x squared. So that's what that looks like. I subbed in negative x for x. But if you notice, both exponents that are associated with these are positive, so that would realistically just make it y equals x to the 4th minus 4x squared again, because a negative number to a positive exponent makes it a positive number. So that checks out. So that's y-axis symmetry. So you would check the box y-axis. So we tested for it graphically and we tested for it algebraically by plugging in negative x for x. All right, let's look at number 2 now. So number 2, I'm looking at this. I'm going to look across, is it overlaid across the y? Nope, because if it was, I'd have something up here. Is it overlaid across the x? No, because I'd have something here. Does it look like I've taken this and rotated it around a central point 180 degrees? And that answer looks like yes. So I'm going to test for origin symmetry. So if you go back to your original sheet, or the notes up above, you can see that the algebraic test for origin is to replace x with negative x and y with negative y. So let's try that. We're going to test for origin. So I'm going to plug in negative x for x, negative y for y, and then a negative number times another negative number equals a positive number. So I'm just going to result back in xy equals to 6. So that checks out, and that's origin symmetry. Some of you might be having a little bit of a hard time because we're working with variables and not with numbers. But if you need to sub in a number to see if it's still going to work out, feel free. So like for instance in this, if I had x equals 2 and y equals 3, 2 times 3 equals 6, if I do negative 2 times negative 3, that's still going to give me positive 6. So that's still going to check out for origin symmetry. All right, let's look at number 3 now. So number 3 is this weird circle. And again, I'm going to look, does it look like it's folded over the y-axis? It's not even folded over the y-axis. It's not even rotated 180 degrees, but it does look like those points here. It does look like it could be folded over the x-axis. So let's see if it is. So in order to solve for that, we have to plug in negative y for y. So I'm going to plug it in for x plus 3 squared plus negative y squared equals 16. Again, we have a positive, we have a even number exponent with a negative number, so that's not going to change the value of that number at all. So this is really just going to be the same equation as the original, plus y squared equals 16. So that checks out for x-axis symmetry. Okay, so again, if you are stuck on this just using the variables, try and plug in a number that you're comfortable with working. You can even try 1, and you know that -1 squared is still +1. So you know that value is not changing by making it negative. So number 4 is a little different. So let's check this one out. It looks like we got our two V's, one going up, one going down. When I look at it folded over the y-axis, it does look like it can do that. When I look at it folded over the x-axis, it also looks like it could do that. And it also looks like I could have taken this and rotated it 180 degrees and gotten to this graph also. So it looks possibly graphically like all three, but let's just test for x and y first. So for x-axis, I plug in a negative number, or I plug in negative y for y, and I can see that that's already y squared, so I know that it's going to pass x-axis. For y-axis symmetry, I plug in negative x for x, and I have x squared, so I know that if I plug in any number there, that's the opposite sign. I'm still going to get back to x squared. Like if I had 2 squared and I plugged in -2 squared, I'm going to get 4 for both of those. So that checks out for y-axis symmetry. And because I can plug in both negative y and negative x and get back to the original equation, I also have origin symmetry. So if you have both of these symmetries, you also have origin. So let's look at that really quick. So I'm going to plug in negative y squared minus negative x squared equals 1. Negative y squared is the same thing as y squared. Negative x squared is the same thing as x squared. That equals 1, so that checks out. So that's x-axis, y-axis, and origin symmetry. All right, let's do the last two. So this side's a little bit dirty, so I apologize for that. And I erased this. All right. So number 5, we've got the y equals the cube root of x minus 1. And it doesn't really look like, y-axis, it doesn't look like x-axis, and it doesn't look like origin, because if I was to rotate this point 180 degrees around, the direction of the arrow, the slope would be different. So it doesn't look like any of those. So I'm just going to say none right away, because graphically it passed that it wouldn't work for any of those. So if I was to rotate this 180 degrees, my slope would be different than that. It wouldn't fit directly in there. So you can try and do it with your hands too. So like you can see like the bump here is like out like that. If I was to rotate that in, the bump would be over on this side. It wouldn't work. All right, last one, number 6. So let's look at this one. So again, doesn't look like y-axis. I mean, doesn't look like x-axis, doesn't look like origin, but it does look like y-axis. This side, I've got a point here, and it looks like I'm just taking the opposite x value on this side, so I'm just changing the x value. So it looks like y-axis symmetry, so let's try. So we'll plug in negative x for x. So y equals negative, the absolute value of negative x. And what is the absolute value of a negative number? It's just the positive number. So fy equals the absolute value of x minus 2. So nothing changes, so that is y-axis symmetry. All right, so I would encourage you to pause it and look through these answers. So we got for number 1, we got y-axis symmetry. For number 2, we got origin symmetry. For number 3, we got x-axis. For number 4, we got x-axis, y-axis, and origin. For number 5, we got none. And for number 6, we got x-axis, or y-axis, sorry, y-axis. All right, so the last thing on this worksheet is determining if a function is even or odd. So a function is, a function is even, so a function is even if it's symmetrical with respect to the y-axis. So this is on your note sheet. So a function is even if it's symmetrical with respect to the y-axis. So this is y-axis symmetry. So if I was to do an algebraic check of this, remember that I'm subbing in negative x for x and getting the same answer. So if I'm going to write this in function notation, I'm going to say f of x equals f of negative x. Just like that. So f of x equals f of negative x. And what that's just saying is that when I plug negative x into the problem, I get the same answer as when I plug positive x into the function. So a function is odd then if it's symmetrical with respect to the origin. So a function is odd if it's symmetrical with respect to the origin. So this is origin symmetry or point symmetry, and how I would check for that algebraically is I would write f of negative x equals negative f of x. So that, because this is what happens when I plug in negative x and negative y, this is the same thing as negative x and negative y. Negative f of x is the same thing as negative y, and then this f of negative x makes it so I'm switching both positive x to negative x and positive y to negative y. All right, if that wasn't confusing enough, let's do a few examples. So really important here is this algebraic check. So for even symmetry, f of x is equal to f of negative x. And odd functions, f of negative x equals to negative f of x. All right, let's do a few examples. So the first step in solving any of this is to solve for f of negative x. That is the common function that's shared by both types. So remember, if it's even, it's f of x equals f of negative x, and if it's odd, it's f of negative x equals negative f of x. So let's solve for f of negative x first, and then see, so we check to see if the answer is equal to negative f of x, and if it is, then that's odd, or symmetrical with respect to the origin. And if the answer is equal to the original f of x, then we know that that's even. So first step is to solve for f of negative x and then see, is that equal to what we get when we multiply negative 1 times the original equation, or is it equal to the original equation itself? So let's see. Solving for negative f of x. So in number 7, we got x to the third, f of x equals x to the third minus x. So we're going to do f of negative x here, and we're going to get negative x to the third minus negative x. And so what I get when I do that, negative x to the third is just equal to negative x cubed, and then negative x, or minus x, is equal to plus x. So I got f of negative x equals negative x to the third plus x. And so now I check my second step. So this is my first step, is to solve, and I did. So I solved, and I got negative x to the third plus x. And then I check to see, is that answer equal to negative f of x, which is negative 1 times the original equation. And it is, because x to the third times negative 1 is negative x to the third, and negative x times negative 1 is plus x. So this is equal to negative f of x, which makes this odd. And so this is, we also have to describe the symmetry. So this is odd with symmetry about the origin. So that is the answer, origin there. So that is the answer to number 7. So let's try number 8 now. So our first step, solve for f of negative x. So f of negative x here, and we get so we have f of negative x equals negative or negative sign times negative x squared plus 6. So we have equal to negative x squared plus 6 when I simplify. And if I look at that, negative x squared plus 6, so that equals f of x. So this is even. So I check to see if the answer is equal to negative f of x or if it's equal to f of x. And this is equal to the original equation. So I'm going to say that this is even and symmetrical about y-axis would be my answer for that. So this is even symmetrical about y-axis. So that's what makes these two different. 7, I got negative 1 times the original equation. So negative x to the third plus x is negative 1 times this original, or negative f of x. And in number 8, I got the same answer as the original equation, which means that it's equal to f of x, which is even and symmetrical about the y-axis. So you can try number 9 on your own. I'm going to do it right now, so you can pause the video and get a jump start, and then check your answer once we're done. Okay, so in number 9, first step is to solve for f of negative x. So I plug negative x in, and I get negative x to the third minus negative x squared minus 2 times negative x. And then when I simplify this, I get negative x cubed plus x squared plus 2x. Actually, minus x squared there, because that's x squared and then it's subtracting it. So I did my exponent first. I actually excellently jumped ahead in PEMDAS. So now I'm looking at this. This is times negative 1 gives me that. That's the same, and that's different. So this is going to be none, because this does not equal the original equation. Times negative 1, and it doesn't equal the original equation. So that's not even or odd. It's neither. All right, let's try number 10. Solve for f of negative x. So that equals negative x squared minus 4. So that equals x squared minus 4, because negative x squared is the same thing as x squared. So this is the same thing as the original. So f of negative x equals f of x. So we know that this is even and symmetrical about y-axis on that one. All right, last 2 and then we're done. So in number 11, I have negative 8 over x. So I solve, first step, solve for f of negative x. So I plug this in. Negative 8 over negative x equals 8 over x. So I have f of negative x equals to the original equation times negative 1, because negative 8 over x times negative 1 equals positive 8 over x. So I have f of negative x equal to negative f of x. This is odd and symmetrical about origin. All right, last one. So I have f of x equals the absolute value of x plus 1. All right. Solve for f of negative x. So equals negative x plus 1 absolute value. And this does not equal this. This does not equal this times 1. So this is going to be none. Because f of negative x does not equal f of x. And f of negative x does not equal negative f of x. So it's none. It's neither. All right. So feel free to reach out with any questions. Again, we had our answers for 7 is odd, 8 is even, 9 is neither, 10 is even, 11 is odd, and 12 is none. Remember, our first step is to solve for f of negative x, and then check to see if it's equal to negative f of x or the original equation f of x. All right, I will see you in class.